Segment 4, Intermolecular Attractions and the Properties of Liquids and Solids. All right, so we're talking about phase diagrams, and then we started to get into the types of solids when I took a delayed moment to pause. So picking back up with that, then when we look at solids, the first thing we're looking at is crystalline solids, and these are going to be solids with a highly regular arrangement of components. Now, not all solids will be crystalline. They can also be amorphous. Now, an amorphous solid is one where there's considerable disorder in their structures. So you can think about it as they start to crystallize, little fragments of crystallization start everywhere. They're all different patterns, and so it becomes a weird non-repeating pattern. Versus if I were to get everything to order from one end to the other, then I'll get a more crystalline nature. So crystal structures have regular patterns. So if you think about a wallpaper design, right, and packing of atoms in a crystal, we call that a lattice. So what a lattice would be then is the repeating of the unit cell. Typically it's going to be regular and highly symmetrical in the system. It's going to be in 3 dimensions, right? So it's a 3-dimensional system of points designating positions of components. And of course, we can look at this as atoms, we can look at this as ions, and we can look at this as molecules. So all 3 of these will then form these regular repeating patterns in the solid, and we can look at that regular repeating pattern, we call that the lattice. So we start with a basic unit cell, right? So the unit cell would make a box. Okay, it's the smallest segment that's going to repeat regularly. The smallest repeating unit of our lattice. Now here we've made it nice and square, so it's very easy to see. Now the 2-dimensional unit cell, where it can get a little confusing, so we call that our unit cell. And then you can see if I put a picture in there though, what we get are the weird parts of the corner going into the picture. All right, so 3 types of the 3D unit cells. There's the simple cubic, so we simply just have a cube. It has 1 host atom at each corner. Okay. The edge length then, A, would be equal to 2 times the radius, where R is the radius of the atom or the ion. Now, our second cubic center, cubic structure would look like this. So now you can see we have an atom at each corner, but now we also have one in the center. We call that a body-centered cubic cell. It has 1 atom at each corner and 1 directly in the center. The edge length here is going to be A equal to 4R over the square root of 3. Okay. Our last one gets even more crazy looking. So now our unit cell, right? There's our square there. There's our cube. We go into 3 dimensions. If I look at just one face, you can see now we have one right in the center of the face of our cube. Then if I look at the next center, I've got one there. If I look at the next center, I've got one there. Center, one there. Center, one there. Finally, the bottom, we have one there. We call that our face-centered cubic cell. Each one has an atom centered in each face and 1 at each corner. The edge length here is going to be 4R divided by the square root of 2. Now, whenever we have packing, we call that closed packing of spheres. If we take a look at our first layer, right? So here they are, edge to edge, going across. Then they're offset so that we can fill in that empty space there with the next edge. And then they'll offset again, offset again. When we bring in the second layer, all right, so the most efficient arrangement of spheres in 2 dimensions. Each sphere has 6 nearest neighbors. And when we bring in that second layer, you can see now they're kind of like ball to ball, if you will, so the edge to edge. Now the second layer with atoms and holes on the first layer. Now, there's going to be 2 ways to put on a third layer. So as we grow, there's going to be a couple ways to do this. Directly above the spheres in the first layer, so here you can see it's right next to each other, or above holes in the first layer. So we can either be the same height or we can be down one, right? Those would be our two options. So the cubic lattice then is our three-dimensional array. So now how they sit is going to depend on where they are. It's kind of weird. They're going to sit the best way to minimize the amount of space in between them, and that's what's going to give us our three different types of packing, right? So our 3D simple cubic lattice means they're all edge to edge, okay? None of them are like sliding down to fit into those faces. I've got models at school. That's not going to help us here. I should have brought them home with me. So I can put them up in the camera and you can see a little bit easier how this is fitting together, right? So there's our unit cell, our space filling model. Then when we do our unit cell, you can see we have the corner edge of each one of the atoms. And so the direct center is going to be empty. So if I move to the other cubic lattice, right, so here's our face centered, and now you can see when we do our unit cell how we have half an atom here, the other half would be in the next unit cell. Or if we do a body centered, then what we end up with is one full unit in the middle of our cell, and then the corners would all be an eighth. Now, ionic solids, the lattices of alternating charges. So these were all atoms so far, right? Only one thing there. Now we're going to look at cations next to anions. So here we want to maximize the electrostatic attractive force, right? And we want to minimize the repulsion. So it's going to be based on one of the same three lattices. We're still going to be based on a simple cube, right? And so it's going to be either a simple cube, a face-centered cube, or a body-centered cube. So our common ionic solids are going to be sitting like this, where we have our cation being really small, our anion being large, and of course this is going to be our sodium chloride here. So rock salt or sodium chloride. We have a face-centered cubic lattice. And here you can see we're going to let the chlorine be the face center. And then inside that lattice is where each of the sodium atoms are going to fit. Okay, so the sodium ions are going to be the octahedrals in the holes. So now other common ionic solids, cesium chloride. Here we're going to put the chloride in the center. The cesiums are all going to be on the edge. Zinc sulfide, and of course calcium fluoride. So you can see it starts to get complex. Now spaces in ionic solids are going to be filled with the counter ion. Right? That's always going to be true. So in sodium chloride, we see the sodium is going to end up being the center, and then we'll also end up with partials on the edges. The chlorines are going to look like they're going to be face-centered. And that way the sodiums can fill in the empty spaces of the chlorine. Now count the atoms in the unit cell. You should have 6 of each, or a 1-to-1 Na plus Cl minus ratio. Right? So again, you can count all your different spheres, whether it be halves, eighths, or a full sodium, and you should end up with 6 of each inside that cell. Now, counting atoms per unit cell. So your site, if it's a body, it's going to count as 1. So if it's body-centered, then you're going to get a count of 1. It's shared by 1 unit cell, right? If it's face-centered, it's going to count as a half, and it's going to be shared by 2 unit cells. If it's on an edge, it's going to be a quarter, and finally, if it's a corner, it's going to be an eighth. So 4 types of sites in the unit cell. So central or body position, atom is completely contained in 1 cell. The face site is where it's going to be a half, and then the edge, if we go back and take a look, so here you can see you have an edge where the top part of the atom is missing, and then the one side of the atom is missing, and so what we have left is a quarter. And then finally our corner will be the 1/8. So now if I want to look at a sodium chloride and I start counting up my cells, for sodium we see one we have right in the center. So we have a body center that gives us a count of 1, but there's no chlorines in the cell, that's a 1, right? On the face, we have no chlorines. We only have, we have no sodiums, so that's going to be 0. but we do have 1, 2, 3, 4, 5, 6 chlorines, each one worth a half. That gives us 3. All right, on the edges, we have our sodiums, 1, 2, 3, 4, 5, 6, 7, 8. All right, so determine the number of each type of ion in the unit cell. All right, so for cesium chloride, we've got 1 to 1. For zinc sulfide, we have 4 to 4. And for the calcium fluoride, we have 4 to 8. Right, so notice the ratios have to match up to what the structure is, right? So zinc is 1 to 1. So it's 4 to 4 inside the cell, right? So we have 1 on each corner. So that's 8 and 8 corners. That would give us 1. And then we have halves for all 6 faces. That's 3. 3 plus 1 gives us 4. And then for the zinc itself, all 4 of them are inside the cell. They're all quartered. All right, for the calcium fluoride, you can see we have 8 on the corners for the calciums. And then we have face centered again, so that's going to give us 4. And then we actually have 1 in each quadrant for the fluorines. So 1, 2, 3, 4, 5, 6, 7, 8. All right, the factors that affect the crystalline structure, of course, would be the size of the atoms or the ions involved, the stoichiometry of the set, what the actual ratio is, that lowest common multiple, and of course the materials involved, right? Subsubstances do not form a crystalline solid. Now for amorphous solids, things like glass, right, they have little order and thus are referred to as supercooled liquids. The edges are not going to be clean, but they're going to be ragged due to the lack of order. Now, we can also use different methods to figure out what the solid looks like. X-ray crystallography has become very common. So X-rays are passed through a crystalline solid. So what you'll do is take your material, get it to crystallize, take a single crystal, put it on the diffractometer, then bombard it with X-rays, and then we'll take a look. Some of those X-rays will be absorbed, but most of them will be re-emitted in different directions. Okay, based on those emissions, the atoms are either going to be in phase, others could be out of phase. But what we'll do is we'll record that emission on film, and from that, we'll be able to figure out what that structure was. So for instance, if I have an X-ray source, I shoot the X-ray out, it's a single beam, it hits that crystal, it's going to give me some sort of pattern. And we can go out and measure that pattern. Okay, so that's your experimental setup, that's your diffraction pattern, and then what we'll do is interpret that diffraction data. So as the X-ray hits the atoms in the lattice, they're going to be deflected. The angles of those deflections relate to the lattice spacing. And so then we can estimate the atomic and ionic radii from the distance data. It involves the Bragg equation. No need to worry about that. But you can take a look at it if you want. For those of you that enjoy the math and the equations, you may. This will not be on the test though. Just the concept of what X-ray diffraction would be, not actually using the Bragg equation. Let's see, the diffraction pattern of copper metal was measured with X-ray radiation of wavelength of 131.5 picometers. The first order Bragg diffraction peak was found at an angle theta of 50.5 degrees. Calculate the spacing between the diffracting planes. Again, that's not something I'm going to ask. All right, let's see. Using diffraction data, X-ray diffraction measurements reveal that copper crystallizes with a face-centered cubic lattice. What is the radius of a copper atom expressed in picometers? All right, so now this is actually a little something that would be common, right? So this is going to just be basically a geometry problem. So if we're looking at the cell, X-ray diffraction measurements reveal that copper crystallizes. So we're given a cell length, so we know what the cell length is. And then it's asking what is the radius of a copper atom expressed in picometers. So we have our cell length. Now we just need to figure out what the radius would be. All right, so we'll use Pythagorean's theorem here, so we can make triangles out of that. Get a squared plus b squared equals c squared. where A equals B, which equals the 362 picometers. The C is the diagonal. So 2 times A squared is equal to C squared. And of course, plug and chug through that. And so we get the radius of the copper to be 128 picometers. All right, so learning check. Silver packs together in a face-centered cubic fashion. So they've given us our nice pretty diagram. The interplanar distance, d, corresponds to the length of a side of the unit cell and is 407 picometers. What is the radius of a silver atom? So if we go back and look, we know that A is going to be equal to 2 times the square root of 2 times R. So we know that 407 is going to equal that. Working backwards, R is going to be 53.6 picometers. And again, those last two questions, the geometry problems, that's more like what you should expect on the exam, not worrying about the Bragg equation and diffraction patterns. All right, so ionic crystals have cations and anions. At lattice sites, they're relatively hard. They have high melting points. They're brittle. They have strong attractive forces between their ions. They do not conduct electricity in their solid state, right? So if we put salt in water, then the salt will pass a charge. But as a solid, sodium chloride does not pass a charge. So they will conduct electricity well when they're molten, though. All right. Iridium crystallizes with a face-centered cubic lattice. The atomic radius of iridium is 175 picometers. Determine the unit cell length. All right, so you might have had to go back and pick up that equation. So you'd have to go all the way back to where we looked at the cell lengths. We know the cell length is going to be based on the radius. They gave us the radius. We can plug and chug that, and we get 495 picometers. So that came from the diagonal of the cube, which was equal to 4r, where r is the atomic radius. So the diagonal of the cube then would equal the square root of 2 times a, where a is equal to the side of the cube. So we just plug and chug that, and we get 495 picometers. All right. So covalent crystals then, this is lattice positions occupied by atoms that are covalently bonded to other atoms at neighboring lattice sites. So they're also called network solids, interlocking network of covalent bonds extending in all directions. Covalent crystals will tend to be very hard, have very high melting points, and have strong attractions between the covalently bonded atoms. So a network solid would look something like that, where it just continues to go. Here's diamond. So all carbons, right? Silicon dioxide would be another one. Alternating silicon and oxygen atoms. So this would be the basis of glass and quartz. Silicon carbide, also same boat, right? Those are all network solids. Last but not least, we have metallic crystals. The simplest models basically have positive ions from the metal and then an electron cloud that just doesn't seem to belong to any one metal ion. The lattice positions of the metallic crystal occupied by positive ions, and the cations again are surrounded by like a cloud of electrons. They're formed by valence electrons and extends throughout the entire solid. So metallic crystals then are very good at conducting heat and electricity. For them, it's the movement of the electrons. They have luster characteristically associated with metals, so they'll be nice and shiny. All right. Their loosely held electrons will vibrate easily, and they'll re-emit light with essentially the same frequency and intensity. All right, classify the following in terms of most likely type of solid. So, pulverizes when struck. It's non-conductive of heat and electricity. So we know that's definitely not metallic, right? Non-conductive of heat and electricity. Pulverizes when struck. So that's going to be molecular. It's a white crystalline solid that contains electrical current, conducts, not contains, conducts electrical current when molten or dissolved. Okay, and so that's going to be ionic. Shiny, conductive, malleable with high melting temperatures. And of course, that's going to be metallic. So again, similar to questions that might be on the exam, I'll give you a description and then ask you which type of solid it is. Right? Now, molecular crystals can contain all of the listed attraction forces except, so dipole-dipole attractions, electrostatic forces, London forces, or hydrogen bonding. Well, since it's molecular, we know we can't have ions there. If there's no ions, right, we lose the electrostatic. All right, that concludes the chapter. So good luck. This is our last chapter. So the only thing left now is going to be the exam, fourth exam. So best of luck to you. If you have questions about this stuff, feel free to contact me, whether it be an office hour or set up an appointment. I'd be more than happy to talk to you about any of these topics. Again, as we were going through the slideshow, I pointed out some of the things that will most likely not show up on your exam. They've never been on the exams before. I don't expect them to be on there anytime soon. Again, the biggest things out of this chapter that I want you to know really well are going to be the phase diagrams and then determining the type of solid. So know the differences between your ionics, well, that's basically the moleculars, the covalents, and the metallics, and what differentiates them. All right, best of luck to you. I'll talk to you soon. Have a good one.